In this first exercise for our class, we want to talk about mapping landforms in a very basic sense with applications to geomorphology and earthquake geology. This one focuses on simple mapping, and hopefully also will teach you a kind of a interpretive sequence where we start with more of the observations and try to then go to more of the interpretations and try to always come back to that. And so this was something I did, and I've developed more broadly and have applications for a couple of places in California. But this exercise that we're doing for our class is just for Wallace Creek. So you can see where it is in California along the San Andreas Fault. But before we get into Wallace Creek, what I want to talk about is morphological mapping. And it's so basic, I think some people are like, wow, this seems so trivial, but it's kind of like a simple language of morphology where each of the elements that we map is kind of like a letter that we use to build up the words for the landforms. So see if you like that analogy. This was originally I found this paper by Savagear, who is a British physical geographer who laid down this idea. But that basic idea is if you take a landscape like the one in the middle here, and let's not worry about the geology so much, let's just worry about the morphology. And so we see that it's comprised of these different segments of slope, of hill slopes and channels, and those are separated by certain transitions. And so we have like flat to kind of rolling over to a cliff, to this slope with some kind of a micro slope in it, and on down to the flat to the slope, and then this channel. So that's the description, but how do we document it? What are our words so that we can give, and our letters, our language, our graphical language that we can use to systematically characterize this landscape? And so here's a suggested one that he had, which is these kinds of, angular convex break of slope. So that's right here on the map, which would be what that break would look like. And you see the steep slopes on the edge of the channel. This is this kind of little teeth on one side where it's pretty sharp. You can see that then when it's the other pattern, which in other geologic maps we might think is a thrust fault, but here it's an angular concave break of slope. So that would be this one here, and concave meaning it's like upward facing in terms of the opening. Whereas you see this one be downward facing, so that's why that one's convex. And we see the cliff has this kind of somewhat ugly rampart looking pattern. So this is the idea. And then these the gray just shows these zones of steeper slopes between 5 and 40 degrees. So again, trying to give us this graphical representation of this landscape. So let's go. So that was 65, and then by later, modified in 75 and even later, is this map. And so here it's kind of like, well, what kind of mapping do we want to do? So again, we have this landscape now. It's a little bit more complicated than we saw before, and has some geology in it. So we can see it's some dipping layers, and then some landforms like this landslide, and I forgot what this funny thing is, and then the channel, and then a little kind of valley fill, this gravel that's filling the valley. So again, we can go back to our morphological mapping symbols and map just the shapes of the landscape. And that is kind of what we want to do in this exercise as the sort of beginning step. But from a morphologic map, we can go to more interpretation. And so there's geologic map, morphogenetic map, process map, hydrological map. The geologic map, we would add more information because we might, go in the field and say what the rock types are that we see. Some of these other ones are a little bit more kind of like the morphogenetic map is how did this landscape get to be the way it is. So it's kind of a genetic meaning how it formed. But a lot of interpretation there. Process map, here's what processes are operating over this surface. And so TR is like a transitional landslide. And hydrologic is kind of what's the water doing. So, it's kind of always the first question you want to ask is what kind of mapping? And so let's start with a morphological map. And so we're going to do that at Wallace Creek along the San Andreas Fault, which is a really famous place with clear evidence for active faulting. It's basically a plate boundary. And so our goals are that you'll have some basic skills in handling base data and then using those information to map, to delineate landforms. And so the tasks are you're going to load a bunch of these base maps in QGIS, make a morphologic map and then a geomorphic map and identify the major tectonic landforms. So there's this kind of progressive interpretation from just base data to morphology to naming things and putting where's the fault. And so here we see this sort of suggested morphology, so you could use the patterns that were provided in the examples I had from Savagear or this, which is a little bit of a simpler version. And you can see, so like Sharp Ridge, this little railroad track, this would be, the line would be on the top of that ridge. Whereas this convex slope break is this one, concave slope is this one. And if they're gentle, you might use a slightly different pattern. Trough on the slope, ridge on the slope, flat. A couple different ways of doing drainage, different surfaces. So we want to do lines, points, and polygons. And, you can modify it. You don't have to use this, but just be consistent. And so here's the topography. So this topographic map that you'll produce contours. This is based on digital elevation models from airborne laser scanning from the B4 project. And so it's just contours, but already we start to see things we can interpret. But I want to really push you to use this morphologic mapping idea as a way to force yourself to cover the entire map zone. So we don't want blank areas. And just because there's an area doesn't mean you have to find a fault there. You might only find one fault. But we want to still map where, everywhere we can to, indicate where the slope breaks are. So we see this flat valley here with kind of a sharp upper break and a sharp lower break. Those two sort of feed into another set of breaks. So this ridge line here. So we just want to work through systematically with our language and just start marking. And so again, it's kind of like the exercise of doing this is almost more valuable as a process because then it forces you to look everywhere. And what I show here then is just a couple to try to get you started, where we kind of show the upper and lower breaks on the either side of that depression. And so that's the first step. But then if you do it where you turn off your base data, you can start to see this abstraction. So this is the morphology of the landscape. And then as we progressively interpret, as we move to the right, then we can say, okay, well, this looks like this is a valley bottom. So I can put a polygon there. And finally, I put the fault in. So I think it's very important that you keep mentally thinking that faults are late in our interpretive process. You don't start with the fault and work backwards. You're like, oh, well, here's the fault. I guess I need to draw this offset channel. It's more like, no, let's define what's here. What are again, this kind of letters that make up the words that make up the paragraph of this landscape, and let's progressively abstract and then interpret. It's extremely important that you do it. And you want to have also even level of detail. So this is me doing a quick demo. I think you could have a little bit more detail, but you want to have whatever level of detail that you employ, it should be even across the entire map. So don't leave blank areas, because if there's a blank area, we don't know if you looked there. So you want to always find something to map in every portion, but you don't want to have too many lines too close together. So kind of even mapping. If this was a piece of paper, what I'd like to say is every thumb print on the map is where I'll put at least one observation. So because you're doing this digitally, you kind of have a variable scale, a lot of times, or zoom level, but you kind of want to try to keep it at a constant zoom level so that your line density stays about even. And so here's an example of just another view of that same area from when I did this on a chalkboard once. And so you can see again some of the lines. So you can see this this railroad track here is catching the top of that ridge right there. And here I'm trying to do the top and bottom of these slopes that are sort of bounding this little valley, and so forth. And then I'm interpreting, then I put that sort of valley floor in. You could map other features, ridge tops if you want, that are, you think, representative of some polygonal, domain. And then finally, again, in red here, I'm showing where I put the fault. But I waited to the end to do that. So I think it's very important to have that progression of interpretation. And then finally, you could play around. If you have a piece of paper, you could cut it along the fault and think about reconstruction. And then as a final point, just one of the parts of the assignment is to name some of those features. So this is a classic kind of 3D model of this landscape that's dominated by strike-slip faults. And so there is a sort of designation of some of these names of features. So this would again be at the end of your interpretation sort of workflow. You would start to mark and label and name things. And here's just an example of that in another part of the San Andreas Fault, where I tried to show what those things are in this particular landscape.